Hi, I'm Himasha and welcome. Today we are demonstrating a production-style distributed messaging system which we built for our module SC2062. What makes modern data platforms so resilient? How do they stay online even when things go wrong? The answer lies in core distributed system principles like fault tolerance, continuous, and synchronized clocks. This was a team effort and I like to introduce the developers who made it happen. Sandali led our fault tolerance layer, building the heartbeat system and failure detector. Sasindi implemented the core Raft continuous module, and Shadursan architectured our replication strategies. And myself, I focused on the time synchronization subsystem. We built a fault-tolerant distributed messaging system that combines a Raft continuous layer, Quorum-based replication, and an NTP-style time synchronization subsystem. The platform is implemented in Python with an AIOHTTP server, as well as SQLite for local persistence and a React dashboard for observability. Its goals are to provide a high availability, strong consistency, and globally ordered message delivery, even under failures. Over the next few minutes, each team member will cover their module, and I will hand over to our next member.
At the heart of our system is a small Raft-based cluster made up of identical nodes. Each node can take one of the two roles, either as a leader or a follower. The leader coordinates all client writes, while followers continuously replicate the leader's state. We used a three-node cluster setup, which is ideal for high availability. So even if one node fails, the remaining two can continue processing requests. Raft ensures that there's always one valid leader at any moment, which keeps the cluster consistent and avoids the conflicts. Now let's talk about the data flow from message submission to final storage. A client can send a message to any node in the cluster. If that node happens to be a follower, it will respond with an HTTP 307 redirect, automatically guiding the client to the current leader. This happens behind the scenes, so no user input or manual reconfiguration is needed. Once the message reaches the leader, it is added to the leader's log and then replicated to all followers using the Raft append entries RPC. When a majority of the nodes confirm that they've received the message, the leader marks it as committed, which means that the message is now safe even if the leader fails right afterwards. Finally, the committed message is stored permanently in each node's SQL database, making the system durable and fault tolerant. Let's move on to fault tolerance module, the part which I worked on most closely. Our goal was simple but ambitious, to make sure the system stays online and consistent even if nodes fail or lose their network connectivity. We defined two key requirements. Guaranteed message delivery, which means once a message is acknowledged, it should never be lost. Secondly, continuous service availability. The system should automatically recover from failures, ideally with a sub-second failover. Now let's talk about, to achieve these goals, we'll have built several key mechanisms. Now let's talk about them. First is message redundancy. We support two replication modes. Asynchronous replication, which focuses on performance, so around 300 messages per second with latencies under 25 milliseconds. It is fast, but it offers eventual consistency. Then there's synchronous quorum replication, which focuses more on reliability. The leader will wait for a majority of nodes, that is n divided by 2 plus 1 nodes, to acknowledge before committing. It is slower with around 85 milliseconds latency, but it will guarantee zero data loss. But both modes rely on a unique message ID that is stored in the database. This provides duplicates during re-entries or synchronizations, ensuring exactly only once delivery. Next, we have the failure detection. We used a two-layer heartbeat system. First of all, there's the Raft heartbeats, which is every 200 milliseconds, which is used for rapid leader detection. And then there's the application level heartbeats, which is done every 2 seconds, which is mostly used for general health monitoring. And if a node is unresponsive for more than 6 seconds, it is marked as failed. But we used adaptive timeouts to avoid false alarms during brief networks or slowdowns. And then there is the automatic failover. which is used when leader failure is detected. The system will automatically trigger an automatic failover. And here's how it works. If a follower misses a few heartbeats, it assumes that the leader has failed and starts making a new election. The Raft algorithm makes sure that the most up-to-date node becomes the new leader. The leader election process usually completes within 300 to 600 milliseconds. On the client side, this process is completely invisible. If a client sends a request to an old follower during a failover, that node simply responds with HTTP 307 redirect to the new leader. And in our React dashboard, this is updated in real time to show which node is the leader. So users can actually watch the leadership change and a change happen in real time without actually any downtime or message loss. Now let's talk about what happens when a failed node comes back online. When a node rejoins, it runs a rejoin sync process. It compares its last saved message index with the cluster and requests all the message it missed while offline through the sync API. These new messages are applied using the same deduplication logic. So even if a message appears twice, it is actually only stored once. This process ensures that every node eventually reaches the same consistent state as the rest of the cluster. Now let's look at some three key recovery metrics. There's the failure detection, which is done. This is how long it takes for the system to be certain that a certain node has truly failed, not some network lagging. Here we use a slightly conservative timeout to avoid the false alarms that are caused by network latencies. While the Raft itself can detect a leader loss in under a second, the failure detection takes around 5.2 seconds. Then the leader election, which is done in under 450 milliseconds. Once a failure is confirmed, the Raft steps up to elect a new leader. This process actually finishes in less than half a second, which means client experience almost no noticeable downtime in write availability. Then when a failure node comes back online, it automatically catches up on all the missed messages in just over 2 seconds, becoming fully synchronized and ready to serve again. Let's see how our system dashboard actually captures our distributed message systems, node failure handling and recovery all automatically. As you can see in the first snapshot at the top left, everything is healthy. Node N0 is the leader and both followers are connected and is stable. The dashboard shows that the replication mode set is to asynchronous and quorum of 2, meaning all nodes are actively communicating. In the second snapshot at the top right, we simulate a leader failure. You can see that N0 has switched to a candidate stage, and this means that the Raft protocol has detected the failure and is starting a new leader election. During the short transition, this replication mode temporarily shows as unknown, since the system is reconfiguring itself. Finally, in the third snapshot at the bottom, it is fully recovered. A new leader has been elected. The followers have reconnected and the dashboard confirms everything is back to normal with zero data loss and no manual reconfiguration is actually needed. So these three stages are healthy state, election and recovery clearly demonstrates our system's automatic failover, quorum-based consensus and the continuous availability, all visible in real time through our dashboard.
Alright, let's talk about one of the most important parts of our distributed messaging system, data replication and consistency. This module ensures that every message sent by a client is safely copied across multiple nodes in the cluster. So even if one node fails, no data is lost and the system keeps running smoothly. Our main goal here was to make replication both fast and dependable while maintaining strong consistency between nodes. We designed this part of the system using a leader-based replication model. Think of the leader as the manager of the cluster. It handles all write operations and ensures followers stay up to date. We implemented two replication modes, asynchronous and synchronous replication. In Quorum mode, a message is only confirmed after a majority of nodes acknowledge it. This ensures zero message loss for committed entries. We have also added deduplication, so if a message is retired, it's stored only once. Overall, this setup gives us strong data consistency and stable performance even under heavy load. Now, let's see how these replication strategies actually work. In synchronous replication, the leader waits for the responses from a majority of followers before confirming the message to the client. It's slightly slower, but it guarantees durability even if the leader crashes right after committing. In asynchronous replication, the leader acknowledges the client instantly and then replicates data to the followers in the background. This makes it super fast with low latency, which is perfect for high-performance system where speed is top priority. This slide shows how our system automatically selects a leader node for replication. On the left and 0 acting as a leader running on port 8000 with async replication mode. So you can see its current term and leader URL showing its handling all write requests. On the right, we have a failover node which is synchronized with the leader to keep its data updated. And the bottom, the cluster connection panel shows the communication status. If a node fails, it's marked in red, and once recovered, a new leader is automatically elected. This quick election process ensures replication continues smoothly without data loss or downtime. During testing, the asynchronous mode gave us really impressive performance. Average commit latency was around 25 milliseconds, and the system achieved throughput of 300 messages per second. That's excellent for a 3-node cluster. There's a small trade-off though. If a leader crashes suddenly, there's a 3 to 5% of risk of losing unreplicated messages. So async mode is ideal when speed matters most, and a tiny bit of risk is acceptable. With synchronous replication, we focused more on reliability. Here, the leader waits for at least 2 out of 3 nodes to confirm his message before committing it. This slightly increases latency, about 85 milliseconds on average, and throughput in 120 messages per second. But the key benefit is zero message loss. Even if a failure happens right after commit, all acknowledged message remains same and consistent across nodes. We also looked at how efficiently data is stored. Each message takes up to 1.2 kilobytes. So far, 3-node cluster with 10,000 messages, total storage used was about 35 megabytes, which works out to around 11.7 megabytes per node. That's extremely lightweight and scalable for larger deployments. So, the data replication and the consistency module is the backbone of our distributed system. By combining asynchronous replication for speed and synchronous replication for durability, we achieved a system that's both fast, reliable, and fault-tolerant. Even if a node fails or leadership changes, replication continues seamlessly, keeping our data safe, consistent, and always available across the cluster.
Now, I will explain how I implemented the time synchronization subsystem for our distributed message system. So for our main objective was to produce a globally consistent message timestamps, and some of the key requirements for that included to maintain a clock synchronization across all nodes and ensure temporal ordering of messages, as well as to provide accurate time synchronization. So these are some of the core components that I implemented. Some of them included to provide correction strategies and a message ordering buffer that maintains logical timestamps order, a periodically synchronization with the live peers, as well as per peer measurement and validation. So here, this is the time sync panel of our React dashboard. At top left, you can see the delivery matrices and time sync block. Here we display the average store latency, average correction magnitude, and the sync accuracy. To the right is the peer offset list. It shows the per peer offsets and the delays. And at the bottom, I've included a terminal log snippet that shows the actual sync rounds. So together, this just gives like a live view of the clock alignment and how peers compare to each other. In this, highlights the operational features, and a manual sync that triggers immediately runs a synchronization round. The green success box is what the UI returns after the sync completes, including an offset and an accuracy. So these are some of the core measured results from our 60-second evaluation. The before column shows the raw unsynchronized state. The average clock offset for that was around 45.2 milliseconds. And after running the synchronization rounds, the average offset dropped to about 6.3 milliseconds. These numbers show that our medium-based offset and drift compensation meaningfully and tighten the clock agreement across nodes. So here are the message received and stored with corrected timestamp. Top left shows the sender message UI, and the right shows the replicated message log. This is how the system actually guarantees the consistent ordering, even if clients or network delays can cause like skewed timestamps. So for our performance overhead, for the CPU usage, the background sync uses like less than 1% additional CPU, and for our latency, the timestamp correction adds about sub-millisecond processing per message. As for the network, each sync rounds exchange only for like few hundred bytes per pair, and for our failure handling, per pair handling syncs uses like a consecutive timer for like 5 seconds in code. So overall, the sync subsystem gives millisecond accuracy with minimal resources cost. And
Now let's take a look at consensus and agreement algorithm. Our consensus layer is built on the Raft algorithm, which ensures that all nodes agree on the same ordered log of messages, even during failures. It keeps the system consistent and reliable, even if one or more nodes go down. So, why we use Raft algorithm for our application? Simply, Raft algorithm is simpler than Paxos algorithm for implementation. Moreover, Raft operates in two key phases, leader election and log replication. The leader sends heartbeats every 200 milliseconds to confirm it's active. If followers don't receive those heartbeats within 300 to 600 milliseconds, they start an election. Now let's take a look at consensus performance. First up, leader election. So, during leader election, a candidate requests votes from the other nodes. Once a majority responds, the certain node becomes the new leader, completing the transition in under a second. This quick process ensures continuous availability with minimal downtime. During normal operation, the leader handles all writes. Each message is appended to its local log and replicated to followers through append entries (RPCs). When a majority acknowledges, the message becomes committed and is safely stored in the database. The diagram below shows how the Raft algorithm elects the leader from all the current available nodes. So then, if we talk about the failure, it means reliability and recovery of this algorithm. This mechanism guarantees that every node maintains a consistent and ordered log, and that no committed message is ever lost, even if the leader crashes. If failures occur, Raft algorithms built-in recovery automatically synchronizes nodes, bringing the cluster back to a healthy, consistent stage. Our dashboard shows key runtime settings like a 200 millisecond Raft heartbeat for quick failure detection, a 300 to 600 millisecond election timeout to avoid split votes, and periodic 30-second time sinks for clock accuracy, all tuned for stability. Let's take a look on key configuration parameters of this system. Our system uses a 200 millisecond heartbeat and a 300 to 600 millisecond election timeout for quick, stable leader changes. Time synchronization runs every 30 seconds with 5-second buffers for ordering and failure detection, ensuring smooth and reliable operation. We integrated each module step by step and tested them with PyTest simulations and manual fault scenarios. The dashboard verified real-time leader changes, replication status, and message ordering. The system achieves over 500 messages per second, leader election in under 1 second, and sub 10 millisecond clock accuracy. Optimizations like batched RPCs and synchronous tasks keep it smooth under load. In short, we built a resilient, consistent, and self-recovering distributed messaging system combining fault tolerance, replication, time synchronization, and consensus for high reliability. Thank you.